Okay, we're going to get started with our first course example, and that's finding the MPE for a continuous wave visible laser. We will then compare the MPE to the output of a 3 milliwatt laser pointer. Now remember, the MPE is our safe biological level. It's the amount of laser light or concentration of laser light we can be exposed to, and if we're at the MPE or below, there is no hazard. There will be no change in our biological tissue. What I want to do is start by using the database, and the database is just simply another sheet to an Excel workbook that we use to store the input parameters. So I'm going to go up here to add-ins. I'm going to say load PDB from file, and PDB stands for personal database. I've already called this up. It's in a folder I call course examples. This is the database, and you'll notice it's a .pdb extension, so I'll double click it, and it loads in all the course examples or hazard analysis of the course examples that we'll be looking at. If I want to load the input parameters of the first row here, which we call a record. So every row is a record. So this is record 1, record 2, record 3. I click somewhere on the row that I want to load. You'll notice it's highlighted. I go back to the menu and I say load parameters from PDB record. And it puts the parameters in. So this is our 635 laser. It's in nanometers. Let me just show you this very quickly. This was the data description type, which is MPE example 1, but if I click that cell, I get a form up that I'm able to load a considerable more information in. And this is for the report form, and then to be able to just store various pieces of information that you've collected either from an audit or from literature and descriptions of the laser you're working with. This is a continuous wave laser. We select continuous wave. We select average power for continuous wave. Sometimes very seldom do we use energy. Sometimes some people do, but for the most part, continuous wave is average power. We've entered 3 milliwatts here, which the software uses scientific notation because we deal with very large and very small numbers. You can also enter this as 0.003, and you will notice that it changes it to scientific notation. The ANSI default for this is exposure duration is 1/4 of a second. We're relying on our aversion response to work. Then we load in some beam information that we were not given from the slide or the laser information. Now what I've done is I've picked a small beam diameter, and then I use an m² diffraction limit of 1. This is a propagation value that when used, it calculates the lowest divergence theoretically possible for a 1 millimeter beam. So this gives us sort of worst case. And what I'm looking for is I want to make sure I get 100% transmission through the limiting aperture. Right? And the irradiance in the eye limiting aperture, this average irradiance, is what we compare to the MPE. We'll talk about that in just a minute. It is also calculated based on the observer range, which is right here, the observer range, which we have set to 0. So for a small beam set at the aperture of the laser, technically it's the waist of the laser, but for industrial units and what we're talking about right now, we'll say the aperture of the laser. The observer is sitting right at the aperture of the laser, has the eye right up against the aperture of the laser. And for small beams, when we have 100% transmission at the observer range, the OD at observer range and worst case OD will be the same. Now, what we get when we enter the beam information, and don't forget to enter beam information, we find the MPE, the ocular MPE right here. It's 2.55 e to the minus 3 watts per square centimeter, or 2.55 milliwatts per square centimeter. This is our safe biological limit. Notice it is in irradiance. It is being expressed in irradiance, watts per square centimeter. Now we look at our laser, and the way we get the average irradiance in the limiting aperture is we divide the power, 3 milliwatts, by the area of the limiting aperture. We'll show you this in just a little bit. what that calculation really looks like. But we always use limiting apertures in safety, so we're always averaging the laser power over the area of the limiting aperture. That gives us the average irradiance in the limiting aperture of the eye. We use peak irradiance when we talk about single pulse. We'll look at that in a little bit. But right now we see that the average irradiance is 2.8 milliwatts per square centimeter. So it is above the MPE, and therefore we have an OD value. If we select an OD value of exactly 0.486 for our eyewear, then the average irradiance in the eye, once we pass through the OD filter, this average irradiance would equal the MPE. Right. Let's do one thing before I leave this example, and let's do a reality check. The NOHD is the nominal ocular hazard distance. It's how far I would have to back up from the beam in order to look down the beam safely. In other words, if I had a direct eye exposure and I was at my NOHD, I should be right at the MPE level and I wouldn't have a hazard. But let's check that. Let's put our observer at exactly 19.42 meters away, and we'll see that, yeah, the OD at observer range goes to almost zero. We look at the average irradiance in the eye limiting aperture, and you'll notice it matches the MPE. So this is sort of a reality check for software. Right? If I set it at something a little lower, say 18 meters, I'll notice that the OD value is slowly creeping up. Set it at 10, it continues to rise. We'll put it back at 0, and we're back to the worst case OD in this case. All right? So that's our first look at a hazard analysis, the MPE, average radiance in limiting aperture of the eye, and how we use the average radiance in the limiting aperture and the MPE to help us determine if there's a hazard, and then we use both of those to calculate the OD value, which we'll show you a little later. All right, that's the first one.